Okay, hello everybody. Welcome to the MIT Category Seminar. Today we have Rémy Tuyéras from MIT, who's going to talk about a category theoretical argument for causal inference. Hello Rémy, and welcome. Please start.
Thank you, Paulo. So today's talk will be about trying to link category theory to causal inference. And we will do this by using methods from category theory, as well as well-known methods from statistics, and try to merge them into one method. So before talking about this framework where we mix two methods together, I would like to talk about causal inference and causality in general, and just to give a feeling about what causality is. So I tried to find a definition for causality on the internet, and I made a summary or my own definition, and I see causality as a conceptualization of the possibility to assess to what extent an event can lead or imply another event. So it's trying to relate events of reality together and understand how an event can cause another event. And behind this assessment of causality, there's a logic. This logic is usually called Bayesian networks, and it's made of graphs. So it would usually be drawn as a graph. So we would relate events together. So there are two types of events. We have causes. Say we have a cause one that would imply another event that we call effect. Say effect two. And the goal is really to relate events together through arrows. So Bayesian networks are sort of graphs relating events or observations together and trying to organize them in terms of which one appears first and which lead to another. And these graphs can be quite complicated when we have collections of causes and we have to infer diagrams between causes and effects. But of course we can have, causes can be effects too, which means that the graph can be more complexified and we can have causal relationships between causes. And sometimes it's difficult to understand the relationship between causes to effects because some causes may actually control different causes, and it is a question to determine which one appear first in the diagram. So which of the causes are initial in the diagram. And this is one of the main problems of causal inference. And having formal methods to determine that is one of the main goals of causal inference, I would say. So the way it works to determine this graph of connections is that on one side, we have a method with which we can evaluate the strength of these causal relationships, these arrows. And then on the other side, we have the logic, which is made of the graph, which is the graph I drawn earlier. And the interaction between these two models or worlds is interdependent. So we would have a connection between the logic and the method where the logic is guiding the method and the method is summarizing what we found. And so would be connections. So would evaluate connections between cause and effects. So from here to here. And from this evaluation, so usually we have numbers. So say 0.5 or 0.8. And depending on these weights, we would be able to draw a logic from that. So maybe one way to do it would be to have a threshold on the weights we determine for each relationship, and then from that just select those relationships that have a high weight. And therefore, Bayesian networks are cannot infer causality, but instead are used to guide and summarize our analysis. So the point here is that we can't really use this graph language to show that one event is the cause of another event. And today, what I would like to propose is a method that tries to incorporate both sides of the diagram I just drawn between the logic and the method. So incorporate a method within the logic. So if we put this in words, our goal today is to define a category theoretical slash maybe graphical, because I drew a graph, in which we can infer causality. So it would really try to integrate this bridge between the logic and the method inside the framework. So let's see how we can do that. So this slide is telling a little bit more about causal inference and how it is seen from the point of view of probability theory and statistics. So that gives us different ways to work out causality. So let's try to see what probability theory and statistics do about causality and how causality is measured. So probability theory uses deductive reasoning to predict the likelihood of an event from a combination or combinatorial description of possible occurrences of an event. And this hides some non-determinism because the way you are going to encode the event is non-deterministic. It's arbitrary and depends on who is designing the model. So you could have some scenario could be either implemented by a function that would map combinations of scenarios to events of interest. And maybe someone else, another mathematician, could also design another function that would parameterize the space of combinations of events differently. And one example is if you look to the Sleeping Beauty problem on Wikipedia, you'll see that for the same statement of a problem, you can have different interpretations and can obtain different probabilities for the same problem. So that measuring probabilities and also causality requires the mathematician to define events suitably. And this may lead to different assessment of causality in a model. So just to finish, causality usually in probability theory is measured by a difference of conditional events. So usually we would see equation where we try to understand the probability of an event depending on if we do a certain action C compared to what this event is when we do not do the action. And we would try to measure the difference between these probabilities, and that would be a way we can measure inference between the action C and the event E. Now in statistics, it's a bit different. In probability theory, we saw that it was a deductive reasoning. Now in statistics, it's more an inductive reasoning, where we analyze the likelihood of an event from past measurements. And here again, it's non-deterministic, but here the problem is not because we don't know how to parameterize the probability space, it's because we don't have enough data to understand the actual reality or the actual event. So usually we would measure some event and the observations would be this way. And we would stop the measurements here. And therefore that would give us a certain behavior. But nothing guarantees that if we keep measuring this event, what we would have measured would actually be completely different from what we measured before. So what we are going to infer may not be true about reality, and that can be a problem. So here the requirements is that we need to have enough data in statistics. And the way we measure this is using p-values, where a p-value determines whether you can believe in your result, given if you were given the opportunity of continuing measuring the event. And usually p-values, so here I'm going to give the example of an equation used for z-score, where again, we measure a difference between a behavior for a control population, and a measurement for a population of interest, which we normalize usually with respect to a standard deviation, and we would we would compare to a critical value. So we really see that measuring causal inference is about measuring differences between measurements. So what does that mean? So let's go back to our previous diagram where we said we had a logic, and then from this logic, we can guide the method. And before, I showed you two different methods, one using probabilities or conditional probabilities, and another one using a z-score. So let's see what it means to measure causation between two events. So suppose that we have a connection, or we want to assess the causal relationship between a cause and an effect. We have two events and we wonder what is the causal connections between these two events. So for probability theory, we look at a map from say 0 to 1, going to the values for probabilities, saying that either we do an action or we don't do an action, and we measure the effect of this action on the event of interest. Or we also measure the implication of not doing this action on the event of interest. And what we do is we try to assess the difference. So basically we would try to measure the slope of this function I just drawn here from 0 to 1 to the space 0, 1. And similarly, we can draw something similar for statistics. So it's the same idea. We would go from 0 to 1 for either we consider the control of the population of interest that may have followed a certain treatment, and we want to understand how this treatment is affecting the state of a disease. So either a person has a treatment or doesn't have a treatment, and we want to compare the measurements of the samples we have compared to these two conditions. And again, here it's, using the Z-score, we try to understand how this function varies. And that can be represented by measuring the slope of a graph. So why do I introduce these ideas is because if we generalize this to more points, so say now we don't have just either we do an action or we don't do an action, but we have many combinations of possibilities where we have 0, 1, but also 2, and so on. With various measurements for these different conditions. Then it's not obvious how to measure the variation or causality for these events, because it's not obvious how we can draw a straight line for this graph I've just drawn here. So the question is, how do we assess causality when we have multiple combinations of events? And that's what I try to answer through this talk, is by proposing a method that would assess the combination of multiple events and assess the causality of these events with respect to a certain effect. So here's an example where this is used in biology, where this time we would have 3 types of conditions, and we would study the disease state of patients. So patients, if you look at the genome of patients that are in the cells, so you look at the genome inside the nucleus, so every individual has 2 pairs of chromosomes coming from the dad and the mom. And you would have 3 types of combinations. Either you have AA, or AT or TA, or a TT. So A and T are nucleotides that are values for in your genome. They are molecules that encode your genome. And what we want to understand is whether these mutations in your genome can cause the disease. So for these 3 types of groups, we would measure the patients that have these mutations, and we would try to understand the variation of the disease with respect to these 3 groups. And usually in biology, they measure this using linear regression. So again, it's a straight line. The question is, very often we don't have straight lines. As you can see, as I drawn here at the bottom, you can have many combinations of this. So the question is, how do we assess causality when there is not an obvious straight line relating these different groups of observations? So let's try to answer this question. So here, suppose that we go in the other direction. So suppose we have a method and we want to better understand how we construct the logic and how we determine the right combination of causes to produce an effect, which is related to what I was explaining in the previous slide, where we have more than just 2 combinations of causes. This time we have a space of causes, and we wonder how they connect to a certain effect. So the goal is to assume that all events are connected, as shown in this diagram, and to determine which of these connections are actually relevant. So to only discover those that have a strong causality between each other. So the way we do this, and this summarizes the previous slide, is that we would have a effect of interest. So some measurement of this effect. And then we would have measurements associated with a collection of causes. So suppose A0, A1, and so on. And of course, we start with the same space of combinations, but we could have different values for these events. So in my previous example for biology, I was considering mutations in the genome. So these spaces could be the possibilities of having certain nucleotides on your genome. So A, T, TA, and TT. That was my previous example. And of course, the genome is made of 4 letters, so A, C, G, T. So you can make any combination of 2 letters using this alphabet. And what we were doing in the previous example is that we were drawing maps that started from 0, 1, or combinations of events. So here we would start from the set of events AI, which I put here, which are these. And then we would collect all those individuals that satisfy these conditions. And then we would have an algorithm that measures some effect about this population. So here I summarize what we saw in the previous slide, where the first algorithm for probability theory was measuring a conditional probability. And the other algorithm we saw for statistics was measuring a mean or an average for certain measurements in the population. So what are we doing? If we try to draw what we're doing here, of course we have effects. So we have a probability space, and we have a set of events, and we have a given cause. And also we have an algorithm that gives us values for these conditions. And the goal is to formally complete the triangle. So we would be able to say that the cause I is actually causing our effect, the effect we considered at the beginning, if we can complete this triangle into a commutative diagram. At least that would be very nice to have such a diagram. And here, just to make it clear, B would be the arrow from omega to E that associates every combination of events in omega to an associated algorithm measurement. So what I just drawn was what we saw in the previous slides, where we were analyzing what probability theory and statistics are doing. And here I am proposing something a little bit more general, where I give you the effect, and I also give you a collection of causes, and we want to understand which are the most likely to relate to the event, or actually which are the most likely to cause the effect we are observing. So this time now we want to complete the diagram differently, where we have a span and we want to draw an arrow at the bottom, making it commute. The problem with this formalism is it's too perfect. And when you measure data, you actually have some noise in the data, which means that it becomes difficult to complete the span. And you need to find a way to express this triangle in a different way. So it may not be a commutative triangle, but something weaker. And we will see that we can express this in the category of partitions, where instead, so this commutative diagram will be an arrow in the category of partitions, but we will see that to take into account noise, we will replace this arrow in the category by introducing an extra term here that would correct for the noise. So let's see how we do this. So I'm going to introduce the category of partitions. So the objects in the category of labeled partitions, so here I'm introducing labeled partitions. The objects are surjections from a given set S to a set of labels, and the set of label is associated with the object, with the surjection. And the arrows between the partitions or the surjections are commutative diagrams, which are the ones that we saw earlier, which are the spans. Like so. And that defines the category of label partitions. Now, let's see. So now I'm going to introduce a few tools that we will need to define products, because we saw in the previous slide that to take into account noise in the category of partitions in order to model causal relationships, we need products. So let's talk a little bit about products in the category of partitions. So recall that for every function, we have a universal factorization, which is the image factorization, factorizing every function into an epimorphism or surjection, and a monomorphism or an inclusion. And it is universal because for every commutative diagram of this form, and every epimorphism E and monomorphism M, we have a unique arrow lifting this commutative square. So making the two triangles commute here. And we can use this factorization system to define products in the category of partitions. So how do we do this? The products in this category is take two partitions, P1 and P2 in the category of labeled partitions. And we define the product P1 times P2 as the factorization of the product arrow given by these two partitions. So here we would have P1 comma P2 that defines the morphism from S to K times K2. And we would factorize this arrow to get the product, which is here. And the arrow, the epimorphism that we get on the left defines the product. And these products have nice properties because they are idempotent up to isomorphism. So the diagonal and the projection from P times P to P are inverse of each other. All right, so as we can see, there are products are idempotent up to isomorphism. So what we can do is actually define a skeletal subcategory of this category in order to make these isomorphisms identities. And the way we do this is that we force the collection of labels to be fixed. So the trick here is to give a linear order to the collection of labels. And then from this, we can label the labels with integers. So the way you do this is you fix a linear order on the set S that you want to partition. So say the individuals or the collection of combinations of events. So this is S is the space omega. And you're going to transfer this linear order to the set K of labels. And the way you do this is by using this definition where the elements in K are linearly ordered if we satisfy the equation I'm drawing here. And here's an example below where we see that this order is actually, so let's explain. So, okay, so we have a partition and this partition is associating colors to individuals, say, that are ordered linearly. And the order that will be transferred to the set of labels, which means here the set of colors is just the order inferred by the natural order on S, which means that before the first element is green, therefore the first element in K will be green, and then so on and so on. So the second element is red, so the second element of K will be red, and then yellow, yellow, and then blue and blue. And that's how you transfer the order. And after doing this, you can use the definition of ordinals to say that because K is linearly ordered, there is a canonical isomorphism to the set nk, which is the cardinal of the set. So from 1 to nk. And that gives canonical labels to your set of labels. And that defines a functor that is actually a adjoint equivalence defining a skeletal subcategory of your category of label partitions. So the way we do this is that we define the subcategory, the full subcategory of label partitions whose objects are images of the operation R. And in this category, every product is idempotent. And the way we define products, the formula for products would be P1 times P2 is equal to the image of the product in the category of label partitions. So we get a very nice category, which is where products with themselves are actually equal to themselves. So P times P is equal to P. And that makes calculations much easier. So once we have this category, we can start formalizing what causality is. So again, we can model events by partitioning populations. So events here would be partitions. So the idea, so here I'm introducing a definition of embedding problems and the solutions. And an embedding problem can be seen as a causal inference problem. So we would take two partitions A and B, and we want to understand how A causes B. And the way we do this, so let's draw this, A and B. And this defines a causal inference problem. And we say that this problem a solution for this problem is a partition epsilon that creates an arrow from A times epsilon to B. Because remember, there may not exist an arrow from A to B, but we will see that it's always possible to find a certain epsilon that can complete the missing arrow from A to B into an arrow. So it's a correction for the noise that we can, the difference or the discrepancy that we can observe between A and B. And therefore, to formalize that, I will define a set VAB that is the set of solutions for the problem AB, which we define like this. And here I use V because it's somehow it is reminiscent of algebraic geometry. Somehow we could think of this problem as asking if there are solutions for a certain polynomial A times X is equal B. The difference between the real world and what we have here in the category of partitions is that the variety we have here, the set of solutions, will have many solutions. And understanding how these solutions relate to each other and how we can construct certain solutions from others is going to be the topic of this slide. So first, let's try and investigate what are the solutions. So possible solutions are B, because there is a projection A times B to B. There is a projection map. So this projection map gives us a solution already in the variety AB. Because of the property I discussed before, which products are idempotent, we also have AB is a solution in the variety AB. So now we have two solutions at least in this set. And that is a good starting point to construct other solutions. So I'm going to give an example first to better understand what we're doing. So let's take the example where we have a partition A that is partitioning a set from A to G made of letters from A to G. So here S, just to be clear, S is the collection of letters from A to G. And we take two partitions A and say B, let's take this one. Well, B, D, F, and C, E, and G are grouped together. So now to understand what products do is that they refine the groups we have, which means that all the possible non-empty intersections of these groups, which means that the product is equal to A, B, C, E and G, because E and G have always been together, so they stay together, and then D and F. And as we said earlier, this is a solution in our variety for the problem AB. And of course, we have many other solutions. So here I drew a lot of other solutions for the same problem for the variety AB. And they're all solving the problem A times X to B. And these solutions may not be related to each other. So for instance, we can see that so let me gather my thoughts. CD. Okay, so what happens is that yes, so I'm going to show you the connections between A and B. So let's draw the partition X6, which is AF So what I'm drawing, sorry, if this is not clear. So this is partition A, which is our cause. So this is partition A. And then we can put partition B here. And what these solutions are going to do is to cut the groups of A in order to be able to be mapped to B. So which means that we see that, for instance, X0 is gonna cut A from F because in this group here, there's no F. And then here, C and D will be cut from D because in this group, there is no C. And therefore we create more groups that now we can gather differently, which means that we can leave A alone, but now F is isolated from A, so we can relate it to F and D, which is isolated, and we can put C with EG. And that's how we can map it to this. So these divisions are the results of making a product with X6. Okay, so what is interesting now is that we can notice that all these solutions are related through diagrams. So here's a diagram of the solutions I've drawn earlier. And now what is interesting is that we can wonder from A and D, which is always given, how do we construct certain specific solutions, say the minimal solutions such as X5 and X0. And because remember, X is a measurement of noise, so we want to find those solutions that contain a minimal amount of noise. So the way we do this is that we will decompose our products into easier partitions that will help us define what we are doing here. So suppose we take a partition A, B, C, D, F, D, E, F, and G. And we can see that what we explained before with the products, we can decompose this partition into a product where this time only A would be isolated because we have this group. And then we could subdivide this big partition using other partitions, such as BC that gathers B and C together, and all the others are regrouped together. So this partition now would create this group. And we could finally create the last group by multiplying our expression with this partition. And that gives us a way to decompose any partition into elementary partitions where there are only two groups. So the result of this is that any partition can be decomposed into canonical partitions that we can call delta. So suppose delta of a set would give the partition divided the set S from its complementary. And now every partition can be decomposed into the elementary partition generated by the fibers of the partition itself. And now we can use this decomposition to define an elementary step that we saw earlier on in this diagram above. So all these steps can be decomposed by only compressing two groups together. So suppose that we would pass from x1 to x2 by merging these two groups. And the way we do this is by defining elementary contractions that allows us to pass from one solution to another. So here we can define the contraction of a partition between two groups through this formula, which is really only contracting two of the groups of the partition, indexed by J1 and J2. And the formula here says that we gather the groups indexed by J1 and J2. And that gives us an arrow from X to X, contraction of X at J1 and J2 that just gathers two groups together. So it's a very elementary operation. And now how do we define?
So Remy?
Yes.
We are now at 12:45.
Okay, thank you. So now the actual question is, yes, we have this way of contracting partitions, but do they stay solutions of our problem? Because if you take a solution and you contract two of the groups together, that may not be true that the partition stays a solution for our variety AB. And the solution to that, in order to stay within the space of solutions, is to only consider certain indices J1 and J2. And these J1 and J2 are defined here in this definition for reduction. So we define the set LAX, where A is our partition A and X is a certain solution or a partition in general. And we define the set of pairs J1, J2, within the space of indices, where J1 needs to be different from J2. And the trick to staying within the space of solutions is to have this condition satisfied, where the intersection with the EF group of partition A, which means the EF fiber of partition A, intersected with the J1 fiber of X, if it's non-empty, then the fiber of X at J2 intersected with the fiber of A at I should be empty. And if you satisfy this condition, then you stay within the space of solutions of the problem. So this is represented here. And you need these conditions to stay within the space. And if you do that, and you contract your solutions with respect to these indices, then you stay in the space, the variety VAB. Okay, and from that, now we can define a reduction of X of a certain solution. As you can see before in our diagrams, we had sequences, chains of arrows going towards a minimal solution. So that suggests that we define a notion of reduction of a certain solution up to when we cannot reduce it anymore. And that the idea is that we would have, so we start with a solution X, and then we reduce it with respect to the indices we find in the set LA of U. And we keep doing this until the set L of A of the solution is empty, which means that at some point, so we will keep reducing the solution until we cannot reduce it and we only get the same partition. And there's a theorem of completeness for this that says that there will always be a partition whose set LA is always empty. And that shows that the algorithm will terminate, which means that we have an algorithm to find a minimal solution for our causal inference between A and B. So we would have something like this, where we denote the last index of where the set LA is empty, KU, and that allows us to define a special element that is a minimal element. So this element the minimal partition will be called U star, and we can call it the reduced element. And now we have a theorem that says that we can construct minimal solution for a given pair of partitions for a given embedding problem. So this theorem says that if given a linear order on our space of individuals or population and a given causal problem, where we define the fibers this way, and we have a choice function R that satisfies this condition, then there exists a certain partition K R of RAB that can be linked, that is a partition that is smaller than the product of A and B, from which any reduction would provide a minimal solution. So what does that mean? If I draw this, that means that we start from AB, which was a canonical solution for our variety. We can construct a certain partition chi-RAB for which any reduction of this partition will provide a chain of reductions or contractions in which all these partitions will belong to the variety AB, and the last partition is minimal inside this variety AB. And here below, I give a formula for this partition. If you want to see how this partition arises naturally, just go see the mathematical paper where there are a few propositions that explain the steps. But this is mainly the theorem that says we can always find a minimal solution. So we have a way to find what is the minimal amount of noise needed, or what would have been the minimal amount of noise added to the set of data so that we cannot see a certain causal relationship between A and B. And measuring the solution X is a way to measure the causal strength that could link a certain event A to an event B. And I'm almost done. I had another slide that was explaining some statistics, and I think I only have 7 minutes to explain this, so I will go over this slide very quickly. And this slide was explaining that here we can control our solutions for causal inference algebraically, where we construct minimal solutions, but we still have one degree of freedom, which was that when we construct this diagram of solutions, we have many choices of contractions. As you can see here, we can pass from X1 to either X2, X3, and X4. And so how do we choose these? Well, the idea is that we can determine these choices statistically this time. And the next slide was explaining how we can do this functorially. So it was explaining how we can optimize a ANOVA score, which is a statistical method that allows us to measure the amount of noise in a certain solution, or the amount of information. And from this statistical method, we would pick the right partition that optimizes the statistical score given by this method. So the idea was to provide a theorem where for every morphism from a certain partition P1 to P2, so here imagine a morphism between solutions in the variety, what is going to be the variation in the statistical assessment of the measurement of noise within the solution. So it's using a very common method called ANOVA, and ANOVA relies on a score called F. So here I put the formula that is associated with a certain distribution. The distribution itself is not really the point of this slide here. Well, what is the point is that we have this formula is that for every morphism from P1 to P2, we can evaluate the F-score of the domain of the morphism. So it's a statistical measurement of the domain of the partition compared to the statistical measurement, the F-score or F-ratio of the codomain of the morphism, up to some extra terms, which were nu F, which is very close to 1, or could be thought as close to 1, minus a certain term epsilon of F divided by a certain quantity, which depends on, which is the standard deviation associated with the set S and a certain collection of measurements. And this equation allows us to control how we pick the best solution in the variety. And the end of the slide here was explaining that this term epsilon F was a functor. And the way we control the construction of solutions is using functoriality, the functoriality of this functor. And I don't think I still have 3 minutes to explain a little bit the story. So let's see what I can conclude with, because I don't think I would have time to explain everything. Let's see. Yeah, so this functor is actually the result of a composition of 2 functors. So let me at least draw some sort of sketch here where what you do, and you can find this in the paper, is that we can construct a functor from the category of unlabeled partitions to a certain category data that models the ANOVA method, statistical method. So it constructs the data required to do the ANOVA analysis. And then we define a functor from data to R called epsilon. And then we relate partitions to R by just composing and calling this composition epsilon y. And the nice property of this functor epsilon y is that it is always positive. And the way you show this, the proof of this very important property to show the theorem I showed earlier, or the proposition I would say, is that you decompose any arrow in the category data that I showed earlier into a specific subtype of arrows. So it would be a factorization of this arrow into certain arrows called codegeneracy maps or morphisms that are actually the images of the contractions we saw in the category of partitions. And once you do this, you have a very nice formula for the value of these codegeneracy maps. which is positive. It's a very nice formula. And then from this positivity, you just use the functoriality of the functor epsilon to show that this result holds for all morphisms. And that's about it. So the conclusion is that we can control the construction of minimal solutions statistically inside the variety of AB. So to conclude, this is the process. From AAB, we'll construct a certain partition chi-RAB that has certain properties. And from there, for any reduction, we can construct minimal solutions, but we can control these constructions statistically using the F ratio of these partitions, which is compatible in some ways to the functoriality. And that's it.
Okay, thank you very much for the talk. Are there any questions or any comments on anything?
Hi, Rémy.
Hey.
Thanks for your talk. So you started talking about causality in terms of Bayesian networks and do conditionals and this sort of stuff.
Mm-hmm.
And at some point there was this switch to talking about this category of partitions and finding solutions relating to partitions.
Mm-hmm.
Is there a connection, or was that earlier stuff meant to be more kind of an intuition?
Yes, it was meant to be an intuition, and constructing, first explaining causality and then explaining what other domains do, and to explain how what these domains do relate to what I'm about to do in this talk. So it was, at the beginning, I draw spans of arrows, and the span of arrows belong to some category of partitions. So here it would be the category of label partitions based on omega. And it would just to give an intuition that these diagrams, these spans or these commutative triangles are trying to assess a sort of variations that was always the goal in other domains, such as in statistics and probability theory, where we are trying to measure a difference of probability, measure a difference of average. And so measuring a difference between two values combinatorially, as I was explaining here, where when we have more than two values, it's more complicated. So the way we do it is using a function. We want a function that may not try to regress a line, but explain some mappings between causes to effects. And this mapping is... Mm-hmm.
Can you then extract this function from a solution in this kind of partition space? Is that the idea?
So it's not always possible to map the partitioning of the space omega inferred by a cause and the partitioning of omega inferred by an effect in the category of partitions. We never have an arrow that would just I'm going to draw it here. Given a certain even A and B that partition omega, it's not always possible to find a morphism between these two partitions in the category of partitions.
Mm-hmm.
So the way we correct that is by introducing an extra term epsilon that will allow this morphism to exist. It's like a span, if you want, where you have this, or maybe more correctly, it would be a span between A and B. But the idea now is to take the right span where we take epsilon minimal and also statistically relevant.
Mhm.
Rémy, would it, oh, sorry. I think other people have questions, but I'll just say mine since I already started. Would it also instead make sense just to look for spans between A and B, not just A times something to B, but an arbitrary S mapping to A and to B? Would that also be a explanation of B given A?
But then I want to measure the causal strength. And the only way I can do that, or maybe the way I did it, is that I saw in epsilon the information I needed for ANOVA, which was a statistical method. If I had S, I think it would be more difficult for me to evaluate what is the causal strength between A and B. I needed
maybe anything S, if I multiply it by A, it is S again. So maybe every span is of this form or something.
Yes, yes. And that was related to the fact that the variety between A and B had many solutions.
Mm.
So if I go back to here, we see that we can multiply here many times by A.
Mm-hmm.
So it's really about finding the minimal solution for this problem.
Thanks.
And I see Jochen Koch has some comments.
Yes, that was very nice. Many of my favorite topics coming together in a single talk. That's really nice. But I just wanted to make some comments about the combinatorics. That many of these things, I mean, there are classical things in combinatorics. So the UP is just the partitions lattice, and the product is usually called the meet.
Okay.
And I think what you call minimal should be called maximal, because in the poset underlying this lattice, it's the last one in the chain. So that would be max.
Okay, so the order relation is inverse.
So the order goes from the finest to the coarsest.
Okay. All right.
That's the same order as you have for surjections. I mean, you're somehow looking at the coastlines in the category of surjections, and then it's the natural order of the arrows.
Okay. All right. Mm-hmm.
No, but that was just sort of terminology. But what I wanted to say is that you're somehow dealing with the fact that the partitions lattice is not distributive, because if you had unique solutions, unique minimal solutions, that's precisely equivalent to the lattice being distributive. That's adjoint functor theorem. So somehow what you're doing is that you're correcting for the fact that the partitions lattice is not distributive by figuring out how to find the minimal elements. Usually there would be only, in a distributive lattice there's a unique minimal element, but here you find many different because it's not distributive.
Exactly, yes. Yeah, I put that in the introduction of the archive version of the paper.
Okay.
Yeah, thanks. But yeah, I appreciate it.
Okay, are there any more questions or comments?
I have a question. Thanks, it was a really fun talk. I was wondering if these tools can be used to identify confounding variables, and this sort of seems related to David's question, because if I think about a span, the apex is sort of confounding the feet. I was just wondering if you thought about that at all.
Yeah, that's an interesting question. I guess that's a next step. I think so. I would want to believe so. Yeah, that would. So the goal would be to have a nice framework / method where we can answer all these questions. So right now I'm working in Kelly's lab at CCL, where I use this to analyze biological data genetic data. So I have genomes of individuals and I have effects, and I try to understand first the causal relationships between mutations in the genome and disease states. And then I guess the next step would be to answer these kind of questions where I ask whether there are confounding factors or, environment. The environment can also affect the measurements you do. So yeah, that's an interesting question that I would like to address in the future.
Thanks.
Good. Anyone else?
If a quick one, if possible, you use the F statistic here.
Yes.
Does your method look like it will generalize to kind of other statistics impossible, or is there something special about the F statistic in your use here?
Sorry, I couldn't quite get the question.
Sorry, it was just asking whether the F statistic was specific for the application of this method, or whether it looks like it will nicely generalize.
Yeah, so why the ANOVA method, right? That's your question. Why do I use ANOVA specifically, or maybe the F-score specifically?
Yeah, I was referring to the kind of the structure of the F statistic, I guess.
Yeah, so it's all about partitions. So I thought it fitted the problem nicely. So what is ANOVA? ANOVA, you have a population, and then you divide this population into subgroups. So for the population, you have a mean, U, 0, and then for each of your subgroups of the population, you have also an average for each of these groups. And ANOVA asks whether these averages are close to the overall average mu. So it's comparing all these averages to the global one through this score here I showed below. So here you see in the formula, we are comparing mu to the subgroup averages, and then all the subgroup averages to the actual data that we have, like measurements. And it's saying that if the F ratio is much greater than 1, which here, so why 1 is because if we look at this distribution here, we see that after 1, it gets, the area under the curve gets relatively small. Not for this one though, but it's in general smaller. The farther you are from 1, the smaller the area under the curve is, the less likely this situation will be. And we want to detect these less likely scenarios where something is special about the data. And from these special situations, we can infer that there's something happening, a causal relationship, and that's how we measure causality. But here, ANOVA is really about partitioning, and it's very general. It's not using any linear regression or any equation. It's really about partitioning and comparing two values together.
Yes, so sorry, perhaps I should have been more specific. Obviously, this ANOVA is using a normal distribution, null hypothesis. So your S statistics referring to chi-squared. So I just wondered if it would generalize to other null hypothesis.
Yes, no, no, I do need this assumption.
Okay, thanks.
Mm-hmm. It would be nice to have a new method that doesn't have any of this assumption.
Okay, are there any more questions? Okay, doesn't seem there are any more live questions. Of course, you're always welcome to ask in the Zulip chat. So here, I'll post the link. And for now, I'd say let's move the discussion on the line. And for those who want, we can have breakout rooms. Let's thank Rémy again. So thanks, Rémy.
All right, thank you, everyone.
And let's now stop the live stream.